select this graph. So presume it's intended to be a 3D graph that spirals around, tapering off and approaching that line. Maybe it's 2D, I don't know, but it looks 3D. So anyway, it's basically asymptotic behavior. I mean, it's approaching, the value of the function is approaching the value of the line, isn't it, over time? Something similar. Now this is your beloved sine function. This is called cardinal sine. And really, it obeys this everywhere except f of 0 is defined to be 1. Because normally if you plug in 0 in this, it's undefined there. So they plug the hole by just setting it to equal 1, which you can see it fits nicely. So anyway, look at this thing. Think about this in the long run. This is what I really want to focus on. What does numerator do as x is huge? Well, as x progresses, it's going to oscillate up and down to 1 or negative 1, 1 or negative 1 forever. That's all the sine does, right? But then the denominator just gets bigger and bigger and bigger, which is why the whole graph just tapers down and shrinks to nothingness. But it's still going to oscillate above and below 0 forever, just less and less. So it approaches 0 in the end. So kind of different. Okay, we're talking about solving equations now. Here's your two basic rules that you're going to use. And you need to know what these say, but also what they don't say. And by that I mean, if you have two equations with the same base, two power forms with the same base that are equal, then you can set the exponents equal, right? That doesn't say, though, if you had like this, x to the power of b equals y to the power of b, that necessarily makes x equal y in this case. Which, just for the record, if I had like x squared equals y squared, must x equal y? No, one can be positive, x can be positive, y can be negative, right? And so just be careful. The other thing, and I told you before, is like if I gave you this. You cannot conclude that therefore 2 times x equals 5. You have to combine these first to get it so it's a single log, which would be that, not log, but power form. And then the rule applies, and you can say, okay, that exponent must equal that exponent, and you go do it like that, right? So just be careful with these things. Same applies with the logs. If you have log on both sides, a single log on both sides with the same base, then the arguments can be set equals. The symbol here in the middle, by the way, stands for if and only if, which basically means it works both ways. So if I give you this equation, you can rewrite this equation. If I gave you this equation, or you're starting with any equation, you put it both sides on a base, common base. And if I start with this, you can do log of both sides. Or if you can get it to be where it's log on the same on both sides, you can drop the logs. All right, let's get to work. This one, it's easy. You get common base. What's the base going to be? 4. You could use 2 if you wanted to, but 4 is easier, I think. So write the 16 in terms of 4. 4 to the power of 2. And so the right side becomes 4 to the power of 2x minus 6. Multiply exponents. And now we've got it so we can drop the bases, or in other words, set the exponents equal to each other. And subtract x from both sides, add 6 to both sides, and we're done. Okay? Next one. Same idea. There's more than one way to do this. I'm just going to note the fact that if I did 1/3 to the power of 4, that would equal 1 over 81. And then it's that to the power of 2/3. So that right side ends up being 1/3 to what power? And if you multiply 4 times 2/3, you get 8/3. And then over here it's 1/3 to the power of n. So I'm pretty sure when you set the exponents equal to each other, you are done. Okay. Different type of problem now. We're just going to strip everything away from x, one piece at a time. We'll start by subtracting 7 from both sides. Next, divide by the -3. Okay, so we have a log. What's the base, by the way? I think now's a good time to write that down. Because when you get it so you have a log equals a number, you can just rewrite the whole thing as exponential. What would the base be? 10. 10 to the power of what? So this base to that power equals the argument. Now you have an equation you can solve. The left side is 1 over 100, isn't it? Which means to get x by itself, you just need to divide both sides by 10. Or really, I'm going to multiply by a tenth. Since fractions are involved, I think that's safer. And then that still cancels, so you get x equals 1,000th, and you're done. Tell me something real quick. If I ask you log base 10 of 100th, what does that equal? -2, yeah, because 10 to the power -2 is 100th. Now watch. If I took my answer, plugged it in right here, what is 10 times 1,000th? Or 100th? So you get log of 100th, which we already said is -2. And then -3 times -2 is 6, so it's 7 plus 6, which is 13, which means we're right. You should be able to check your answers. All right, this one. Divide by 2. Got a 9 over there, obviously. See if I can do this. And just go and rewrite as an exponential. So 2 to the power of 9 equals x cubed. Now, how do we get rid of that exponent? Take cube root. Although I don't like showing it that way. You can if you want to. I just prefer to use rational exponents. So I'm going to raise both sides to the power of 1/3. And certainly if it's an odd exponent, then it's easy. You just get x from that. And here, you multiply exponents, you just get an exponent of 3, which means the answer is what? Or maybe 8. Now listen, let me tell you what you could have done. You could have, as soon as you got 2 to the power of 9, said, oh, that's 512. It's true. And so here, let's do it a different way. So you have 2 to the power of 9 equals x cubed. This is the way not to do it. I'm not saying you can't, it just, to me, is harder. So you can say, okay, the cube root of both sides. So I'm doing the cube root of 529. And the cube root of 529 not 529, 512. And the cube root of 512 turns out to be 8. But no, that's not the easy way to do it. Even if you left this as 2 to the power of 9, the cube root of 2 to the power of 9, you can simplify that, but to me it's easier just to deal with exponents. So there are alternatives. This is just the way I prefer to do it. All right, next one. 5 by 2 again to start with. What's the base? In fact, I'm going to rewrite it as log base e, just so you can see it. Certainly you don't have to. And so if I write it as an exponential, it's e to the power of 9 equals x, and we're done. Just the act of writing as an exponential equation got x by itself, and so we're done. And it says round the nearest hundredth. Obviously, if we had a calculator, you type it in and get a decimal answer. But as it is, that's it. That's our answer. Now, same properties, but now we're going to focus on the log version. There's all the other properties. On the top right, it has the big ones, the product rule, the quotient rule. The power rule allows you to take the power, move it out in front of the factor, right? Which one do I want to use on this problem? Product rule or quotient rule? Product, because there's a plus sign. Product rule. So this becomes log of the product, which I'm going to need to multiply these binomials anyway, so I'm going to do that now. X times negative x is negative x squared. And then that's 1x, and that's minus 2x, which gives you negative 1x. 1x and negative 2x is negative 1x. And then the constants multiply to be positive 2. Okay, fine. Now from here you have two options. Okay, and I'm going to show you both. One thing you could do is note that you have, a log equals a number. So rewrite as an exponential. The base is 2. 2 to the power of 1 would equal that argument. And boom, you have an equation that works. Or you can change this 1 into a log with the same base, log base 2 of something. So tell me this. So log base 2 of what is 1? Every period is at 0. And that's the danger here. Log base 2 of 1 is 0, because 2 to the power of 0 is 1. I heard someone say the answer here is 2. Right? 2 to the power of 1 is 2. So be careful about that. So I'm saying I can replace 1 with log base 2 of 2 because it equals 1. And let me bring down the left side of the equation. There's log base 2 of that trinomial. Okay. Well, so you made it so you have a log base 2 on both sides. So in this case, you just rewrite it with, set this argument equal to that number over there. Equal to that argument over there. So x squared minus x plus 2 equals the 2 there. But isn't exactly what we got using another method? So like 6 is one, half a dozen another. Whichever approach you prefer, use that approach. I don't know why I can't draw an arrow in the right direction. All right, now to continue, there's 2 on both sides, so it zeroes out, it goes away. So you get negative x squared minus x equals 0. Common factor of x means I should factor out x. The fact that it starts with negative means I'll factor out negative x, leaving what? Good. And then, listen, the next proper step is to set each factor equal to 0. We sometimes skip that step, but I'm going to show it here. So when is this right-hand factor equal 0? Well, that's easy. When x is negative 1. When is this equal to 0? When x is 0. All right, now listen to me. When you solve in log equations, it'll happen sometimes that you do all the work perfectly, but it turns out at least one of your answers you came up with, it doesn't actually work. Okay? And so, what is the domain? Let's get this straight. What is the domain of a normal log function? Look at it. What's the domain? Only the positives, right? And so that's what you need to keep in mind. You can only take log of positives, not 0, not negatives. So just check your answers. If I plug in 0, do I ever get a negative from either one of these? No. So the 0 is okay. That is an actual solution. What about the negative 1? Does it cause a problem? No. Negative 1 here gives you a 1. Negative 1 here gives you what? 2. So as long as you don't end up doing logs of zeros or negatives, they count. So those are our solutions, okay? And sometimes they just won't work out. All right. So you could find these, of course, by tapping the calculator. You can check your answers that way. All right, let's try this one. Which rule do I apply this time to combine the right side? The quotient rule, yeah. So rewrite this as log base 2 of the quotient. And now you can set those two equal to each other. But you got it so it's one log equals another with the same base. And then I would just multiply both sides by that denominator. The left side becomes 5x minus 20. The right side loses the denominator. Add 20 to both sides, divide, and you're done. And this one's easy because when you plug in 6, of course it works. So that is the solution. Okay? What are we going to do first in this one? Michael? Cool. You just said the two sides equal. And then we factor, bring the 20 over, it comes minus 20. And the numbers that need are either 2 and 10 or 4 and 5. Which ones? Yeah. Perfectly 1 and 20 in theory as well, but which one should be positive? The 5. And so what you get is then x equals 4 is one solution, x equals negative 5. Of course the 4 works. Does the 5 work? Yeah, actually. Negative 5 squared is 25. Minus 5 is 20, so it's fine too. Okay? The next one adds a step. We have to use a product rule, so we get log of, and I'm going to go and multiply them. If you distribute the x, you get x squared minus 3x. So basically, after one step, it looks like the last example. So now we set those two arguments equal to each other and solve. Move this 28 over, like the last one. We need 4 and 7 this time. Which one should be positive this time? because we need the smaller one positive. And so you get x equals negative 4 is one solution, x equals 7 is the other solution. And this time, the negative 4 obviously fails. And listen, it fails in both of them, but if it has failed anywhere, then it's not a solution, doesn't count. 7, of course, does work, so that's your only solution. Now listen to me. You've heard the term extraneous solution. I don't like the term. I don't use the term. I want you to show exactly the work I have here. If there's an answer blank, ask for the solutions. The only solution is 7. The idea is we start with this log equation, we transmogrify it, into this quadratic equation, which did have these two solutions. Okay, so there are solutions, but not to the equation we're trying to solve. And we do that a lot because, frankly, we're adept at solving linear equations and quadratic equations, so we try to change other kinds of equations into those. But then, in certain situations, solving log equations, solving radical equations, what you get, although it's a solution to the quadratic, isn't a solution to the original, so it doesn't actually count. So it's not a solution at all to this equation. So I want to see the work just like I have. You should come up with that, but then discard it, and say only the only solution is 7. Okay? That's how I like to talk about it. You try this one. And just for the record, 2 and 3 both work. I have a subtle error in how I show my work. What am I missing? Right here, the product rule says there should be the log of the product. There's no parentheses though, so actually what I wrote is the log of only the 5x. Saying without the parentheses, that's not the right work, technically. Now, as far as how I solve the quadratic, I prefer, if I have a negative x squared, I'll move it to the other side. You don't have to do it that way. The other approach you could have taken is keep this stuff on the left, like so. Bring the 6 over to join it. It becomes negative. And then just switch all the signs. That becomes positive, negative, which is what I got with my approach. So, works either way. And then once again, the 2 and 3 both work. They are solutions. Just for the record, if this expression had been written the other way around, of course it'd be different. We get different solutions then. But you see the 2 and 3 both would have failed in that case. And so just be careful. Make sure you check your answers. But yeah, these are both solutions. Let's move on. All right, listen. We have that 1 in there. That changes things. You have 2 approaches. You can either move that log that's with the 1 over to the other side, and then combine it to be a single log. But once you have that, you'd have a log equals a number. You can rewrite it as an exponential. Or you can just change that 1 into a log base 10 in this case. Okay? And then go from there. Hayden, which approach do you want to take? Christian, which approach do you want to take? Okay? All right, Hayden, you get another shot at this. 1 is equal to log base 10 of what? Now, that is the problem. This method's faster. People struggle with that right there. Sorry, it's 10. Because 10 to the power, log base 10 of 10 is 1, because 10 to the power 1 is 10, right? So, here. I'm going to finish it this way, and then I'm going to show you, I'm going to show you both approaches, all right? So, you can replace 1 with log base 10 of 10. And then you can combine those using the product rule, so you end up with log base 10 of, 20x plus 30? And once again, don't forget parentheses around it. So the right side is a single log, the left side already was. And so fine, you set the left argument equals the right argument, and solve. Subtract 3x from both sides, you get that. Subtract 30 from both sides, you get that. Divide, you get negative 2. Okay? Although, unfortunately, negative 2 doesn't work. You plug it in and you get a negative, so there's actually no solution to this equation. Okay? Let me show you the other approach. The other thing I said we could have done is move this log over to the other side, so I'd have log, and just watch, you can write it down if you have room, if you want to. Bring the other log over like so, leaving the one by itself. This is now the quotient rule, so you get log of the quotient. What's the base? 10, it's common log, so the base is 10. And now you have a log equals number, so write it as a power form. The base is 10, the power of 1 equals that argument. And then go from there. Just I would multiply both sides by that denominator. This is really just a 10 here. So the left side becomes 20x plus 30. That should look familiar. The right side is 3x minus 4. Subtract 3x from both sides, you get 17x. Subtract the 30 from both sides, you get negative 34. X is negative 2. Which once again doesn't work, so there's still no solution. So there's your two options. Whichever you prefer, okay? You try this one. Change the problem to what I have up here, though. Just change them both to be plus signs. What you have in your paper didn't work again. I didn't like it. We had 2 in a row that didn't work. And 3 can be written as log base 2 of what? 8. Because 2 to the power 3 is 8. So once again, you don't have to do this approach. Keep working the other way if you're doing the other approach. You should get the same answer. At some point, the two methods converge. The right side, use the product rule, you get that. At that point, the two sides, they both are just a log, so you can set the arguments equal to each other. And subtract 7, x from both sides, you get 7x. Subtract 8 from both sides, you get negative 2. And divide, you get negative 2/7. Which actually counts, because when you plug it in here, it's you get a positive fraction. Actually, what, 5/7? And certainly when you plug it in here, you get a positive. So we're done. That's the solution. And like I said, if you do the other approach where you got both logs on one side, you end up with the same answer in the end. That's fine. Okay? Questions? And we're going to change gears now. All right, look. This is not like the ones we started with because you can't get a common base. You just can't. So let's change it into a log problem. There's really going to be 2 approaches here as well. I'm going to start by just rewriting as a log. It would be log base 3 of 7 equals x. So doing that got x by itself, except what I want your answer to be, though, is something you could type in the calculator. And I know we won't have a calculator here, but still I want it expressed that way. And most calculators can't handle a base other than 10 or e. So we're going to use the change the base formula, which once again, change the base formula looks like this. If you have a log of the base that you don't like, rewrite it as a log with the base you do like, which can be whatever you want, but we prefer e or 10. Somebody think, how do you use e? You don't have to. But you changed a new base, and so you have log of the old argument over log of the old base. So that's what I'm going to do. I'm going to say this can be rewritten as log of the old argument over log of the old base. And that's something you could type in the calculator. So we'll just leave it like that. Now let me show you another approach. Because frankly, what we just did, it doesn't work well on more complicated problems. The other thing you can always do, is if you have an equation, you can take a log of both sides of the equation, right? And so, since the bases don't match, I'm just going to do natural log. It could be common log, it could be other bases. But I want the answer to have natural log anyway, so I'll do this. Since I have log of a power form, the power rule says I can do what? Power can become a factor. Which that's beautiful, because now I can just divide by natural log of 3, and you get the same results. So remember that taking log of both sides on an exponential is going to allow you to use the power rule, which simplifies things nicely. All right, you do this one. To start with, though, get you this much. Just we needed to get the power form by itself, and then take whichever approach you want. I'm going to show both ways. I already have the one way where you just write the log problem. Log base 2 of the argument equals that exponent. Which once again, they got x by itself, but then I did change the base formula. Took the log of that over log of the base, old base, and that'd be your answer. Notice this is log of a quotient, so you could break it up like that. I don't care. I'll take it either way, but you might see it that way. So now look at this. The other approach I said is take your exponential, take log of both sides, which allows me to apply the power rule, which does what again? There's the x out in front as a factor. And this, I could leave it like it is, or I could split it up into natural log of 3 minus natural log of 5. And then you divide by natural log of 2. Either take this by natural log of 2 and get this answer, or take this but divide by natural log of 2 and get the other answer. So this approach gets you the same place, okay? All right. One more and then it gets ugly. Here, if I want to change into a log, it would be log base e, but that's just natural log. Log base e of 8 equals 2x plus 1. Now I'm going to show both approaches, okay? Here I changed it into a log, and then just subtract 1, divide by 2, and you're done. So it's natural log of 8 minus 1 all over 2. And you don't need to put parentheses around the 8, but you might just remind yourself that, the 1 is separate. Okay? The other approach would be to do natural log of both sides. Okay, here. I'm going to take the same approach. There's a shortcut we can do, but first, let me just move the exponent out in front. So 2x plus 1 moves out in front, and then you're left with the natural log of e sitting there. I need parentheses once again, because it's not just 1 times natural log, it's that whole exponent became a factor. What is natural log of e? Yeah, because there's that other rule. If you do log base b of b, it always equals 1. And so that's just 1, actually. And so the left side is really just 2x plus 1. And then you solve for x, you'll get what we already have there. The other thing you could have done is just realize right here, the natural log cancels base e, because that's a separate rule. Say if you have log base b, let me try again, log base b of the power form of the same base, then that just cancels, and that exponent is just your answer. So I could have just canceled that and just had 2x plus 1 sitting there. That'd be faster. Now, last one for today. This one, it's messier, obviously. And I just want you to appreciate that first method I've been showing you, where you rewrite a log problem. I would not attempt that here. You'd say, okay, just watch. Do not write this down. It'd be log, like let's say I want to use the base 3. So log base 3 of this equals what? 6x minus 3. And it just, no, it gets messy. Now, there is no easy way to do this problem. But I'm going to take the second approach, where I take log of both sides. So write this down. I'll do natural log. Once again, as soon as you have, if you ever have a log of a power form, you use the power rule, which means the exponents move out in front. Josh, what's my mistake? Yeah, because once again, the whole exponent should be a factor, but as it is, only the 3 is multiplied times the log, which is wrong. And over here, only the 4x is multiplied on, which is wrong. It's necessary there. Now listen to me. We've run into this situation before. Your x is kind of tied up in both parts of the equation. So the standard thing is to, first of all, just simplify. Distribute, in other words, so I'm going to distribute the natural log of 3 times the first term and times the second term. Do the same thing over here. Distribute natural log of 2 times each term here. So you want to get it all simplified out. Then you want to get all the x terms together. So I'm going to keep the 6x natural log of 3 on the left side. Bring this one over. It becomes plus 4x natural log of 2. And all non-x terms need to move away. So the 4 natural log of 2. Leave it over there. This one goes over to join it, so it becomes a positive. Okay? Now, you really must get why I did that. You ever tell me why I did that? What did that gain us? But right, so if I have all x's together like that, then what can I do? What do you notice about the left side? There you go. That was what I was trying to achieve. I was trying to make it so one side had a common factor of x. And when you have a common factor, what should you do with it? Factor it out. And by the way, someone in another period mentioned that, oh, you could like combine the logs. Yeah, but that's not what we want to do here. That wasn't the point. And whether the problem had logs in it or not, I would have taken the same approach. That's what I want to focus on. And so you get a common factor so that you can factor that common factor out. That's the 6 natural log of 3 there, 4 natural log of 2 there, when you take the x out. And then one last step. What do you do to get x by itself? Just divide by all that mess. Listen, seriously, watch. If I gave you this equation, what would you do to get rid of the 2? Divide it away, right? And so I'm saying, here you're just going to divide by that. I'm just going to write the final answer. So you have what was on the right side, 4 ln of 2 plus 3 ln of 3, divided by this whole mess. And I'm going to rearrange it, by the way. It has 4 ln of 2 in it, and then that's after. Because we need to talk about simplifying. Do you have a common factor that you can cancel? No. But look at the numerator. Is there a common factor? No, you got 4 here, 3 here. The logs are different, so no. That means you can't cancel anything. Once again, watch this. If I gave you, if you could write it as like 4 times something over 4 times something, then and only then could you cancel a common factor of 4. But we can't do that. So you can't cancel the 4s, can't cancel the log of 2, can't cancel 3, you can't cancel anything. You have no common factor. Now, that is an acceptable answer, but let me show you something, okay? I could, once I get to this point, put that 4 on that 2. I could, couldn't I? So that's natural log of 16 plus natural log of 27, because I put the 3 on the 3. 3 divided by 3 is 27. The denominator would be 16 and 729. You could even go a step further if you wanted to. Apply the product rule. This could be combined to be log of the product over log of that product. This is okay, okay? You just need to appreciate the fact that someone might, the book might show it that way. It might combine it to be just a log over a log, and just leave it like that. We're not going to bother. As soon as you get x by itself, you have something you can type in the calculator. I'm good. All right? Okay. Tomorrow we'll do this one, which is the same kind of problem.